we go. All right, so we are now recording. All right, so thank you. I'm Mike with the LRCC at the SLA. You guys know that you signed up. I had a little description. So we'll talk about how trees survive winter. I think everybody, if you're near a window, you look out the window, you see a tree. Obviously, they're still here. They can't hibernate. They don't go underground. They can't fly south. So we'll talk about what they do to survive a winter. Depending on where you are, I know winters can be kind of harsh. So how do trees get through them without freezing and dying? So one of the things we'll talk about briefly to start off is overwintering. And that's a pretty broad term for what most living things that live in a region with a winter do to get through the winter. Different living things use different strategies. Migration, if they can move south to a warmer area, then they will do that. Hibernation, animals will drop their energy use to kind of survive, get through the winter. They won't consume as much energy. They'll store up fat. They'll drop their body temperature just to keep the essential body functions going. And there's this thing called torpor, which is kind of like hibernation, but it's for shorter periods. It was thought that bears only hibernated, but they actually go into a state of torpor, which is hibernation just on a much shorter scale. Hibernation is usually weeks, months at a time. Torpor is maybe a day or two. If it's going to be really cold, then they'll go into this state to conserve energy for a shorter period of time. And even humans overwinter. We put on extra layers. We try to stay warm. We stay inside. Maybe we eat a little more. We bulk up a little more to get through the winter. So every living thing does some sort of overwintering. What about trees? Well, trees, they do a sort of hibernation. They go into a state of dormancy. But we'll go back about 250 million years ago when the Earth's climate was a bit warmer. There wasn't as much cold areas, and where there was cold areas, trees and plants didn't exist. All the trees were in warmer tropical climates where water was always wet, it was always liquid, and it was always warm. These trees didn't have to think about how to survive the winter because winter was not a factor at all. Over time, the climate started to get colder, trees started to adapt, and eventually they spread up into these climates like we're in now, where they have to do something to survive the winter. Many plants die in the fall and they grow back in the spring. They're perennial plants. Trees are much too big to do this. An 80-foot tree isn't going to die every year and then grow back. It took, maybe 50 years for that tree to get that big, and it can't just die one winter and grow back the next year and do it over and over. So instead they go into a state of dormancy where, like a hibernating animal, they drop all their functions that aren't necessary to survive. They really just focus on conserving the base tree. They don't try to grow. They don't do anything like that. So to understand the idea of energy conservation, we kind of have to talk about how plants make energy in the first place. Plants, as in trees, of course, are plants. So I know this video is how do trees extract CO2. That's part of the process of photosynthesis. And I had a whole bunch of stuff written down. I was going to try to break down photosynthesis, but I figured it would just be easier to let somebody in a video do it because that's not necessarily the focus of the video. So we'll play this quickly. It's a short video.
Team Trees has a goal of planting 20 million trees to help fight climate change. But that begs the question of how do trees fight climate change?
Is it supposed to be audio?
Oh, are you not able to hear that for some reason?
I don't hear any audio.
Nope. Okay. Let's see. I unmuted my. How about now? Is that any different?
A lot of the mass inside the trunk.
Much better.
Oh, okay. I accidentally muted myself.
Long chains of carbon, oxygen,
I'll go
and
back
hydrogen,
about 30
all of
seconds.
the atmosphere, and store or sequester it. Now, if only there were a way for a machine or maybe an organism that could take in CO2 and store it, well, that's where planting trees comes into play. When you look at a massive 80-foot tree, what you're really looking at is a massive structure that is mostly just carbon, oxygen, and hydrogen. Let's take a look at the trunk of this tree. Aside from water, a lot of the mass inside the trunk is composed of cellulose, which is made of long chains of carbon, oxygen, and hydrogen. All of these atoms circled here are carbon, and every single one of these atoms of carbon was once CO2 in the atmosphere. As a tree grows from a small sapling into a massive tree, it's fighting climate change by removing tons of CO2 in the atmosphere, and then using it as a key building block in every single one of its cells. So then, the next question is, how does a tree actually accomplish the extraction of CO2 from the atmosphere in order to grow? Well, the super short explanation is photosynthesis. The leaves of the tree combine CO2 with both water pulled up from the roots and energy from the sunlight, and then turn them into glucose and oxygen as a byproduct. This glucose is then transported throughout the tree and used as energy, and also for providing the molecular building blocks which grow more leaves, branches, rings around the tree trunk, and deeper roots. Here on the left we have CO2 in the atmosphere and water from the roots. In the middle, we have glucose, and then on the right, we have cellulose, which is found in every single one of the plant's cells. This process of turning CO2, water, and energy from the sun into glucose and oxygen, and then turning glucose into cellulose and growing larger and larger until it is a massive tree, is what trees do best. And you can see how all of these carbon atoms in every plant cell of the tree once came from CO2 in the atmosphere. So then, if we want to remove CO2 from the atmosphere to help curb climate change, and knowing that every tree is just a massive structure created from CO2, light, and water, a key solution is to plant millions of trees. And that's where you come into play. Team Trees is asking you to.
So then they just start getting to an ad asking for some money to plant some trees. But essentially, that is the, it's a pretty big overview of how plants make energy and how they use that energy to help themselves grow, which is important to understand how they start to conserve energy. So we will carry on through here.
Team Tree.
All right, so we saw that trees need sunlight. So they start to take notice of little changes of sunlight because this is one of the main driving forces of them making energy. So of course, we know the sunlight changes throughout the year, depending on where you are. Here in New Hampshire, the days are a lot longer in the summer than they are in the fall and in the winter. And the trees take notice of this. As the hours of sunlight starts to decline and the temperatures start to drop throughout the night, the tree sends out an alert throughout itself that it's time to start doing something. It's time to get ready for the winter. This alert is sent usually in August or early fall, and it forms this chemical, the production of this acid called ABA, or abscisic acid. And this ABA causes production to start to slow down. It tells this leaves on the tree that, hey, winter is coming, we're not going to need you anymore, so let's start rolling back on your production. Not only that, but this ABA tells the cell membranes within each cell that it's time to start changing how things work. Cells have membranes that allow certain things in, allow certain things out, don't let anything in. This ABA tells the leaf that it's time to start changing some of this to get through the winter. So this abscisic acid as it's forming and it gets into the leaves, the main thing that gets shut down is the chlorophyll, the photosynthesis, the main part in photosynthesis. Ooh, sorry. So as this starts to change, as we see this chlorophyll roll back, the leaves start to lose its green because chlorophyll is the main green pigment in the leaf. So as that starts to roll back, the production of that starts to go, it starts to fade away. And that's when we start to see the leaves change. So you think of a maple tree, you see bright reds, you see oranges, oaks, every sort of tree that changes their leaves, it goes through some colors. And the orange and the reds you see, the yellows, isn't the breakdown of the chlorophyll itself, this green, but it's actually the chlorophyll fading away and making room for other pigments that are in the leaf that aren't as prominent. Things like carotene and xanthophyll. Carotene is what makes carrots orange. It's also in leaves. So as the main pigment starts to fade away, these other pigments are there. They're visible for a shorter amount of time. And then as those start to break down, the leaf starts to turn brown and eventually it'll fall down. So I have this cool video. We won't show the whole thing, but this just shows the rollback within the leaves of the chlorophyll. These are time-lapse videos of the pigments being pulled away as winter and fall are rolling on. All right, so I'd say you get the idea. You can see how when the green pulls away, other colors are starting to show. And then as those colors are being pulled away, you're just left with a brown, which is essentially just the color of dead cells. When you're raking leaves, you are just raking dead leaves. There's no life to them at all. Come on. So if you look out your window, I'm looking out mine right now, and I can see two big types of trees. There's ones that are green and still have their needles, and there are ones that don't have anything on them. The difference between those are coniferous trees and deciduous trees. So deciduous trees, those are the ones that lose their leaves. Those are the ones they don't have any sort of leaves. Those are your maples, oaks, beeches, any of those type of trees are deciduous. Coniferous trees, also known as evergreen, hold on to their needles all year, evergreen, because they are always green. Those are your pine, spruce, hemlock, anything like that. And they both have some adaptations they use to get through the winter. Deciduous trees use a mix of a sap production, which is almost like an antifreeze, and abscission, which is just the process of dropping your leaves. Coniferous trees only use sap accumulation, and that's how they get through. They build up sap in the trunk itself and in the needles. Evergreens keep their needles for years at a time. It takes a lot of energy to make one needle on an evergreen tree because they have this like sort of waxy coating on them. So instead of dropping the needles and expending energy to regrow them every year, they just put a little energy into pumping them full of sap so they don't freeze. And they're actually able to photosynthesize a little bit throughout the winter because those needles are still there. There's two ways you can tell conifer from a deciduous. One, in the winter, coniferous trees have needles where deciduous trees don't. And evergreens are also in a conical shape. So they're, you look at this tree here, it's kind of a cone. You look at a Christmas tree, mostly those are spruce trees, and they are in a cone, which helps kind of shed snow off of them, which kind of lets them photosynthesize a little bit. Those needles are exposed to the sun throughout the winter. If you think of leaves and needles as solar panels, if you got a little snow on top of a solar panel, it's not going to function. So a little bit of snow on these needles, it can't do anything. So that's just one way it helps kind of get the snow off. So what little production they do, they can continue doing. So I said that all deciduous trees drop their leaves and coniferous trees hold on to their needle all the time. And those are the two classifications. That's true, but there are some trees that fall somewhere in the middle, and those are mostly beech trees and oak trees. They hold on to their leaves throughout the winter, and that's called marcescence. So what happens is they hold on to their dead leaves all winter. And there's a couple hypotheses as to why they do this. There's really no proven reason they do, but there's three pretty accepted reasons they do this. So the first one is protection from browsers. If you think of deer, moose, anything like that, they come around and they're tall enough to just pick little buds off of trees. That's what they eat. If a tree has leaves on it hiding those buds, either the deer has to work a little harder to get around the leaves, or it doesn't see them at all. If you think of, you have two bowls of Hershey Kisses. One of them is unwrapped, and the other bowl, they're all completely wrapped. Which one are you going to grab? You're probably going to grab out of the bowl that's unwrapped. You don't have to do that little bit of effort. It's easier for you to just eat one. That's the same thing as the deer. If they have to wiggle around these leaves to eat the buds, they're probably just going to go to the tree right next door that doesn't have any leaves and doesn't have to work around them. Another hypothesis is strategic decomposition. So beech trees and oak trees are known to grow in not the best places. They grow in silty, kind of acidic soils. There's not a lot of nutrients to them. And typically, as we know, trees will drop their leaves in the fall. And these leaves will break down, they'll get worked into the ground, and they'll become fertilizer for the tree. Well, it's kind of thought that beech and oak trees hold on to their leaves come springtime, so they'll drop them in the spring when the new leaves start to grow, and these leaves will bundle up at the bottom in the spring, and it's extra fertilizer right there for them when they need it, instead of running the risk of maybe having their leaves get blown away in the fall, in the winter, somebody raking them up or something. So that was one thought. That's not the most accepted of these three theories, but it is one that's worth mentioning. And the last hypothesis is they're just stuck in evolution. They're trying to catch up, but they haven't gotten there yet. They don't know that the cool thing for all the deciduous trees to do is drop their leaves every fall. They're just a little slower behind. They're still holding on to theirs. Funny, actually, well, I guess not funny, maybe depending who you are, but oak and beech trees are in the same family. They're in the beech family. And within the beech family, there are actually some evergreen trees. So maybe there's some internal conflict going on with these trees. They don't know where they belong. They're stuck in the past. But those are just three ideas as to why maybe they hold on to their leaves. So if you're ever walking through the woods, you're driving down the road and you see a tree with some leaves on it, it's not sick, it's doing it on purpose. And it's pretty easy to tell what they are. If you know what a beech leaf looks like and an oak leaf looks like, and you're walking through the woods in the winter, you're able to easily pick out what kind of tree it is. I know tree identification is kind of tough in the winter because you're relying only on bark. It's a lot easier in the spring when there's leaves, but you can make it easier for yourself knowing two trees already, then why not? All right, so this is a very obvious fact, but water freezes. Well, what does that have to do with trees? Well, trees are made up of about 60% water. And like us, like every living thing, their cells consist of water. So when the trees get into freezing cold temperatures, and if their cells were to freeze, that's essentially a death sentence. If the cells freeze, ice crystals, they're really pointy, it could just puncture the cell and it could kill them. It can make everything leak out. And that's not good for any living thing to have your cells freeze, but especially trees. So they come up with some adaptations to fight that we'll talk about in a second. But I just wanted to note that water freezing inside of a tree, inside of the cells, is bad news. This internal freezing in the cells is called intracellular freezing. So I mentioned before that the alert that makes the abscisic acid, that ABA, changes the cell membranes. What it does is it tells the cells that it's time to start pumping out water and it's time to start dehydrating themselves. So there's not necessarily water inside of the cells to freeze. So you can see on the top right, this image, it's a bit cartoony, it's a bit foolish, but I think it gets the point across pretty well. That shows intracellular as well as extracellular freezing, which is their adaptation to fight that. You can see there is a snowflake inside of a cell puncturing the edges where there are some snowflakes in between the cells that aren't puncturing anything. That's one of their adaptations. Their other adaptation is they come up with a sort of antifreeze to keep the inside of the tree from freezing. They've also made some adaptations to their pipes within the trees, their nutrient transport systems, and they also have thick bark to kind of act as an insulation layer and protection from the cold of the exterior tree. So before we really get any further, we'll break down the parts of a tree. So this is a cartoony cross section, but I think it gets the idea across pretty well. It shows the parts of the tree. You've got the heartwood, which is old xylem. The terms I'm going to be throwing out in the next few slides are xylem and phloem. So the heartwood is old xylem. The sapwood is new xylem. I'll explain those in a second. And then you have a ring of phloem, which is bark that isn't quite bark yet. And then you have outer bark, which is dead phloem. So this is a bit of a cellular photo of the inside of a tree. So you have the xylem here at the bottom, and all those little tubes are the water and nutrient transport systems. So this is how water flows from the roots to the leaves of a tree. These inner rings, so the first and second year, those ones, those are older pipes. They're not as productive as, say, the third or fourth year pipes. The fourth and third year ones are the most productive. That's where the most water and nutrients are going to flow. But the older ones also, they transport some water as well. And then we have the phloem. This is where what we think of as sap, the sticky stuff, flows. Most tree scientists would consider every liquid that flows through a tree to be sap. But to make it simple for when I mention sap for the rest of this, I'm talking about the stuff that flows through the phloem, the thick stuff that we think of, the stuff that gets on your car, that gets on your hands, it's all sticky. That's what I'm going to consider to be sap. And that all flows in this outer ring, this green phloem ring. And as this phloem starts to age, of course, a tree grows from the inside out and pushes things out. As that starts to age, it gets pushed out to the outside. That's what becomes the bark. So the older the tree, the more old phloem there is, the thicker the bark. And it's the same thing with the xylem. These are actually the rings of a tree. So if we look at this image, all these rings here in the middle, those are water and nutrient transport systems. Those are the xylem. And this thick ring around the outside, that kind of dark brown, is the phloem. That's where all the sap that we're going to talk about flows. That can go up and down, can go up through all the branches. And then the stuff you see on the outer edge, what we think of as bark, is just old phloem that no longer has a function other than protecting the inside of the tree. If anybody has any questions about that or anything we've discussed so far, this would be a good time to ask before we get too far in. If not, we'll just keep on rolling. Can you see my mouse moving around? Cool. All right. Well, we will keep on going then. All right. So we talked about what the cells do and how they kind of get by. So I briefly mentioned extracellular freezing. So I mentioned also before that cells are full of water. They're just these little bags of water with some other important things inside of them. But just for the time being, just think of them as little bags of water. So that chemical reaction that was sent out in the early fall tells the cells that it's time to change its membrane. It's time to start pumping this water out so it doesn't freeze. That's one of the adaptations, is the less water there is inside of the cell to freeze, the less freezing potential there is. And this is when the change in the cell membranes, the change that was told by that alert, is really important. This is where water is allowed to now flow out of the cells into the space between the cells. If this happened in the middle of the summer when these cells really need the water, they would shrivel up and die, and the tree itself would die. But during the winter, it's okay for the water to not be in the cells. And as the water is getting pulled out of the cells, it leaves behind a sugary substance that's pretty thick. It's a lot more difficult to freeze. It takes much lower temperatures. So that's what's left. If otherwise, the ice or the water inside of the cells will puncture the cells, as I said, and that's no good. So if you look at this image here on the right, talked about the cell membranes. If you look at it, this is a bit more biology than I'm used to, so bear with me. But there's these two little structures of cell membranes. So you've got a pretty rigid outer one, and then you've got this soft inner one. The ice that's inside of the cells it's gonna puncture this tough outer membrane. It's gonna happen, but that's not the end of the world. If this soft inner membrane gets punctured by the ice, then that's when it's game over for the cells. If it happens too much, then it's game over for the tree itself. So trees have come up with ways to, this is one of the ways they've come up with, kind of surviving. They dehydrate their cells, essentially. Most cases is not good, but throughout the winter, when they don't need as much water, it's okay. These cells aren't producing much. They're just holding on so they can just kind of flatline for the winter and hang on. So the other thing was their pipes, their nutrient transport systems. These pipes throughout the winter, actually, they do freeze, but they've come up with some ways for it to not be catastrophic. So one of the adaptations trees have come up with over millions of years is to have narrower pipes that transport all the water and nutrients throughout the tree. If you had, just say in your house you have 25 pipes and 2 of them burst, that's a pretty bad ratio. That's not good for your house. A tree has hundreds of thousands of millions of these pipes. So if 1 or 2 of them burst, it's not okay, or it's okay. It's not the end of the world. But they've done some other things to be able to survive, to keep these pipes from freezing and bursting instantly at 32 degrees when normal water flows. So one of the ways is by these narrow pipes, based on some physics I'm not really entirely sure about. The narrow pipes are less likely to collect bubbles from air or through any other gas that gets sucked up through the roots with the water. With less bubbles in the pipes, there's less likely chance to have blockages in the pipes. And a blockage in the pipe means nothing can flow. You kind of think of like a heart attack, and you have a buildup in an artery, then things above or below, whichever you prefer to call that, below the buildup start to die, and essentially the rest of you does too. And that's kind of like what a tree does. So their way of fighting this is to narrow the pipes to limit the amount of bubbles. But that's not the only thing that these narrow pipes, do. Of course, it lowers the amount of bubbles, but having less bubbles means the water becomes more pure. If anybody was here for the last program we talked about all about ice. And one of the big things with ice is it won't freeze unless there's a foreign object inside of the ice for the water to freeze around. And that's the same thing with these pipes inside of a tree. So if the water is completely pure and there's no foreign objects in it, the water won't freeze. Pure distilled water can freeze at up to minus 30 degrees if it's under the right conditions, no disruptions, no foreign objects. So having the narrow pipes kind of purifies the water and keeps the water from freezing at a lower point. I found it pretty unique when I was doing research for this. This was an adaptation that wasn't meant for the winter at all. Back when trees only lived in warm climates, and some climates, of course, experience drought, when the trees are working really hard to draw up any water they can through the time of drought, they suck up a lot of gas as well because they're working really hard. If you pump on a well a lot, you're going to get bubbles in your water. So having these narrower pipes pushed out all of the bubbles, they could keep this water transport going, pretty seamlessly. So I thought it was interesting that these trees were pre-adapted for cold weather, and they had no idea that they were going to end up in New Hampshire when they were hanging out down in Florida. But they're ready for it. And so freeze-thaw cycles can cause a lot of damage to the trees. If you see any frost cracks or anything, these freeze-thaw cycles, these big swings in temperature are what's going to cause it, because as the water starts to melt within the pipes, gas does end up getting back into it. And then if it freezes again, then that's all locked in there and it freezes at a higher temperature than it would if it was pure water. So freeze-thaw cycles aren't great. A tree can survive minus 30 degrees throughout the winter. Come springtime, it warms up, all the water melts, and it drops back down to 10 degrees, then the tree's in trouble because it didn't have time to prepare like it would gradually from the fall into the winter. And based on some different properties of trees and under different conditions, I found it interesting. I learned American beech can withstand temperatures up to minus 42 degrees. Sugar maples can go up to minus 45 degrees, and yellow birch can survive up to minus 49 degrees. So if you climb up a mountain like Mount Washington or Mount Mansfield, as you climb, you'll see the layers of trees start to thin out, and the last deciduous tree that you'll see will be yellow birch because they can survive the lowest temperatures. I also read, I didn't include it in here, let's see if I can recall it correctly. Somebody had a bunch of trees hanging around and they had a whole bunch of liquid nitrogen, which is like minus 250 degrees Fahrenheit. They submerged some of these trees in there and they survived perfectly just because of some of the adaptations they have gone through over the years. So obviously, I wish I could remember the specific types of trees. I believe they're types of pines. They have been adapting in cold climates a lot longer than other trees have. I thought that was pretty interesting and maybe a waste of liquid nitrogen, if you want to call it that. So we talked about the trees bursting, the pipes bursting in a tree. If it gets really cold and it gets past that threshold of when the trees can survive, then you may see cracks like this in a tree. This is a relatively young tree, so it'll probably rebound. It should be fine, but it could possibly open the inside of the tree up to cold temperatures, to insects, which is a whole nother can of worms. And I have a little video here. A guy is just filming in his front yard, shoveling his driveway, and he talks about the tree that he found popped in his yard.
Yesterday, I was trying to shovel my driveway. I attempted to get some of it done. And then I heard pop! And the tree cracked. It was so cold. It cracked.
So that video was titled minus 33 degrees causes tree to crack. So obviously that white ash reached its threshold of how cold it could manage. I guess 33 is that period. And it cracked. If you went out on a night when it was minus 30 degrees and you walked out to the woods, you very well may hear it pop, pop, pop. And those are trees bursting. It may not be fatal to the tree, but it certainly opens up the opportunity for ill effects to come down the road. Like I said, insects or just the cold getting inside of the tree. And sometimes these cracks will crack around pre-existing injuries the tree has. So just a weak link with a bunch of pressure put on it, it'll break even easier than a healthy tree, a not damaged tree will. So that minus 30, or as I said with these trees, minus 42, minus 45, 49, is not a blanket statement. That is not by the book, the law of the trees. It's just a pretty generalization. You know, every tree is different, like every person is different, like every living thing is different. They can withstand more or less. So now we can talk about sap, which is one of the other adaptations. It's I don't know if people realize that this is what trees are doing to survive. Sap isn't just a treat for humans, but it's a sugary substance that carries throughout the phloem, so that inner bark, and it carries nutrients throughout the tree. It's really sugary, which is what the tree needs for some production. It helps it grow. That's the energy it gets to grow. So it can go every which way throughout the tree. As you can see from that video, trees are under a bunch of pressure. So whether it's from just the freezing of the pipes putting pressure, or just the growth itself, they're under a bunch of pressure, and that pressure is what drives the sap throughout the tree. If you see any wounds within a tree, so a branch is broken off, or a frost crack, depending on the type of tree, or you put a little tap in it to get maple syrup, that's where the sap's going to flow out. If you think of sap, it's kind of like the blood of a tree. And not to be morbid or anything, but think about, the blood in your body is under pretty good pressure. If you got a little cut on your hand, all that pressure is escaping out through an area of lower pressure, which would be the cut on your hand. So you're going to see blood pulse out. And that's essentially what happens with sap in a tree. If there's a little wound, it's going to go out that easiest to flow area. Some other things about sap that I found interesting. Pine sap, it's golden thick, kind of like what we see here on the left. If anybody has ever seen Jurassic Park and you think of the guy with the cane, the yellow cane with the mosquito in it, that is amber, and that is hardened pine sap. It's a really good preservative. You can find amber from millions of years ago with old ancient mosquitoes caught inside of it, or any sort of bug. And I find that pretty fascinating. Pine sap can also be used as a natural Band-Aid, as well as an antiseptic and anti-inflammatory. And it can also be used for waterproofing. If you were to seal a bench or any piece of wood now with resin, the idea of resin came from pine sap. Resin used to be made out of pine sap itself. Now it's all synthetic because it's easier, it's less harmful to produce than the tree, than taking it out of a tree. But that is where it comes from. It's waterproofing. And if you're really in a pinch and you find a piece of dried pine sap, apparently you can use it as a fire starter. I don't know if that is true or not. I haven't tried. If I stumble upon a piece, then I will absolutely give it a try sometimes. But I thought that was an interesting fact. And then the other thing I learned is that birch sap is highly regarded in some places. Here in New England, of course, maple syrup is going to be the most prominent sap. Why would anybody want to even try something else? But birch sap is regarded in other places. I guess it's good for your kidneys and good for your liver. And it's pretty sweet if you drink just the plain sap itself. You don't boil it or do anything to it like you would maple syrup, which I found pretty interesting. If I ever see a birch tree running sap, maybe I'll give it a try and let you know. But for now, I'm sticking with the maples. And now we get to what every New Englander, or probably every person that's ever had a pancake, knows, maple syrup. This obviously comes from maple trees, specifically sugar maples. And it is, of course, the sap itself is pretty sugary, it's pretty watery, and it can be used for osteoporosis treatment, apparently. And it can also be good to help treat low blood pressure and hangovers, which I found to be very interesting. But that's the untreated sap. That is the stuff straight out of a tree. We all know and love the boiled down maple syrup. So to get maple syrup, I said that pressure is immense inside of a tree. And for maple trees, it's no different. It's a tapper's best friend. And the pressure actually changes throughout the day. You know, coming pretty soon, couple weeks, the sap is going to start to run out of maple trees. And that coincides with big temperature swings. So cold at night, below freezing at night, and warm during the day between 32 and 40-ish is when the sap will flow the best. And that all has to do with the pressure inside of the tree. So as it gets cold overnight, there's a sort of negative pressure within the tree, and all the sap starts to get sucked back up and into the internal tree. And then as the temperatures start to warm up, the pressure gets a little higher, it starts to push out, it gets a little more free flowing, and then gravity takes a hold and it starts to pull the sap down. So I used to think that it was just as simple as when it was warm, the sap rose. When it was cold, the sap went down. And it's actually kind of backwards a little bit. When it's cold, it goes up, and when it's warm, it flows down, which I found interesting. But still, you want those cold nights and the warm days for maple syrup production. Interestingly, I learned, and it just goes to show how little some changes and how beneficial they are. Maple sap is 98% water, and it's 2% glucose, sugar. And I found it very interesting that just that 2% change of the water is enough to kind of keep it going for the whole winter. That little bit of change is enough to keep it from freezing entirely and dying throughout the winter, which I thought was pretty interesting. And so, yeah, this picture here on the bottom right shows I believe it's a spigot or a spout or a tap, if you will, for maple syrup. You drill it into the hole, or drill a hole into the tree. That creates a wound, as I said in the last slide. Any little exposure to from the inside to the outside makes some pressure for the sap to flow out. And so you make a cut in the tree. You give the sap a place to flow out, and you accumulate it. It's a cut in the tree. And I have learned that to boil maple syrup, it's about a 40-to-1 ratio. So 40 gallons of pure maple sap makes 1 gallon of concentrated, thick, sugary, put it on your pancake syrup. So it's a lot of work for some reward. Some people will definitely say it's worth it. Some people will never even touch syrup made out of high fructose corn syrup. It has to be from maple. And I learned about some different strategies to harvest maple syrup that's more land intensive, cutting the tops off of little small saplings and putting a vacuum on the top to suck all the syrup out through the top, which was something I found very interesting. But I guess when you cut the top off of a maple tree, it likes to sprout out the sides. And as those sprouts start to grow, you can cut the tops off of those, put vacuums on there, and eventually you'll have this really sprawling tree that you can keep topping and you can keep sucking sap out of. Now it takes a lot of land because you're planting tons of little trees all around, but there's a lot of methods. You can get lost on the internet, you can get lost on YouTube using that. I had to reel myself back in, and I'll reel myself back in now because we're getting off topic. But there's just a ton of interesting stuff I've learned while doing this. And so we'll wrap it up here. Buds, we usually think of them as a sign of spring coming along. You see trees starting to buds. But these buds actually form throughout the summer. There's expendable energy to start thinking about the spring, 2 whole seasons away. So throughout the summer, these buds form, and they're little hardy guys. They're these tiny little things, but they survive the winter with not much protection, and things like to eat them, of course. So they're covered, you can see down in this little image here, they are covered in these little bud scales. So these give the buds some protection, of course. They're not completely exposed to the external temperatures. They've got a little protection. But the thing I found fascinating with these buds is as these temperature swings happen, they'll open up and they'll let the actual seed inside breathe a little bit. And then when it gets cold, they'll close back in on it and they'll keep it warm, it'll keep it warm throughout the cold night. and it'll just keep doing that. And so that's why there's so many buds. If it was just one seed, then it would probably burst, and then the shrinking and the spreading of the seed itself would damage it. So it's got that little external system built around it. And I think it's just very impressive that these little guys can hold a whole season's worth of growth in them, and they just sit out with not much protection other than a couple little scales for a whole winter, and hopefully they don't get eaten. And they, that's the sign of life. Come spring, we think of trees budding, and we come full circle. The tree grows its leaves back on. It produces as many as it can in the summer, and then come fall, it realizes the sun and the temperatures are starting to drop. The amount of sunlight hours are declining, and we could go right back to the beginning of this presentation and do the winter all over again. And that's just what trees do year after year. The older they get, the better they get at it. But every tree is pretty good at it in some sense. I mean, looking where I am right now, I couldn't even give you a guess at how many trees there are. And they're all surviving the winter. I don't see a single dead tree. So obviously they're pretty good at doing what they do. Trees really, they impressively survive winter without going inside or staying warm or anything. So that is all I have. I want to thank you for joining. If anybody has any questions or comments, thoughts, I would love to hear them. If not, then we'll just wrap it up there.